So we're going to talk about oxidizers, reducers, and assigning oxidation numbers. So first of all, we need to know what oxidation and reduction are, correct? You guys have heard these words before, but probably never actually had to define them. So first of all, oxidation. Oxidation is the combination of an element with oxygen to produce an oxide. What's an oxide? Something that is bonded with oxygen, a compound that includes oxygen. Okay, so for instance, we have carbon plus oxygen producing carbon dioxide. This is a combination reaction producing an oxide. So this would be an oxidation reaction. Okay, another example would be methane plus oxygen producing carbon dioxide and water. What type of reaction is this? Combustion. So oftentimes combustion reactions are a form of oxidation. Reduction is kind of like the opposite of oxidation. They happen hand in hand, but they do two completely things. So reduction is the loss of oxygen from a compound. So, for instance, if we take iron oxide and we mix it with carbon, we're taking the oxygen out of the iron. We're moving it away from the iron, and we're going to get iron plus carbon dioxide. So did we form an oxide? Yes. So did we do oxidation in this reaction? Yes, but we also did reduction. Reduction and oxidation happen hand in hand. It's really hard to do one without the other. So, because saying an oxidation and reduction, they go hand in hand, so we don't have to keep saying that over and over again. This can be shorthanded as redox reactions. Reduction, oxidation, redox reactions. They happen at the same time. Okay? Both processes of oxidation and reduction occur simultaneously. You can't have one without the other. Therefore, we combine them, shorten them, call them redox reactions. All right, so what does that mean for reactions involving oxygen? Okay, well, today chemists use a broad definition that deals with the transfer of electrons. So technically, redox reactions involve oxygen, but there's also a classification of some reactions that do redox, but they have no oxygen. So just because it doesn't have oxygen doesn't mean that it's not going to do a redox reaction. So we kind of expand the definition to talk about electrons. So in an oxidation reduction reaction, we're really talking about the transfer of electrons, not just oxygen. So we have to give new definitions. So oxidation, yes, means you're producing an oxide, but if you're dealing with something that doesn't have oxygen, you are losing electrons. Okay? If it's reduction, what do you think it's going to be? Gaining electrons. Because remember, reduction, usually you get an oxygen removed, but again, if it doesn't involve oxygen, we have to give it a different definition. So this time we're talking about gaining of electrons. Okay, well, sometimes it's kind of hard to remember oxidation versus reduction. Which one's gaining, which one's losing? So there is a shorthand. Leo the lion says grr. Funny, funny, funny. Leo, loss of electrons, oxidation. Loss electrons, oxidation, right? Let me write that for you. Okay, so Leo, loss of electrons equals oxidation. Gain of electrons equals reduction. Leo the lion says grr. This is one way to remember it. What I was taught in high school, I actually was taught a different mnemonic device. I was taught oil rig. This means oxidation is loss, reduction is gain. There are several different mnemonic devices that you can come up with to remember it, but when I started to review this, to teach it to you guys, the first thing that popped into my mind was oil rig from 12 years ago, probably when I was taught it. So you remember these things, and then they stick with you forever. Okay. Okay, substances that lose electrons are oxidized. Substances that gain electrons are reduced. But now we're going to kind of, this is always the hard part. Just like when we were doing limiting and excess reactants, we had a, if I said who was doing limiting, it's different from the limiting reactant, right? Who was doing the excess was different from the excess reactant. So we're kind of going to reverse it a little bit. So substances that are oxidized are called your reducing agent. So they're backwards. So the thing that is, the item that is losing electrons is your reducing agent. So remember, you're being oxidized if you're losing electrons. So that means that it is the one causing reduction. Okay? So the opposite is true for oxidizing agent. Substances that are reduced are also called the oxidizing agent. This is the substance that is doing the oxidizing. So reduction means you are losing an oxygen. It means you are gaining electrons, right? So in other words, that makes you the oxidizing agent, which means you are the one responsible for doing the oxidation. You are the one stealing the electrons. You are the ones removing the oxygen. So that's it. Okay, so this is the part. Easy points are going to be missed on the test, getting these backwards. Basically. All right, so let's see if we can write these reactions. So when you're writing a redox reaction, you almost write it into two steps. So we're going to take the reaction between magnesium and sulfur, and we're going to make magnesium sulfide. Do we have any oxygen here? No, so can we think of it in terms of gaining and losing oxygen? No, what do we have to think of it in terms of? Electrons. So magnesium we know is a metal, which means it is going to, what do metals do in the electron land? They lose electrons. So magnesium is going to lose not one, but 2 electrons. How do I know that? Because it's in the second column. That column loses both of their electrons, right? So what do you think sulfur is going to do? Gain what? It is going to gain 2 electrons. So we are now going to write this into 2 reactions. So basically, the first reaction, we are going to take magnesium, okay, and it is going to be broken down, and it is going to lose its electrons. So magnesium is now going to be 2 plus. Did we lose our electrons? Are they still there? Electrons are still there, so we have to represent them in the equation by writing plus 2 electrons. They didn't go anywhere. They didn't disappear. They're still there. They're just no longer with magnesium. So there's our first half reaction. Our second half reaction, well, we have sulfur now, right? Okay. Well, we know something about balanced equations, right? What do you think has... Remember when we were writing net ionic equations? If they were present on both sides, we could cross them out. Okay, so that same theory kind of applies here. Which side do you think my electrons are going to be on this time? With sulfur. So sulfur is a 2 minus, correct? Well, that's because these 2 electrons are now on that side. Or I guess we don't write the 2 minus yet. And then on the other side, we put the 2 minus. Okay, just to kind of like a, whoever is your cation, magnesium's our cation here, right? Our electrons are going to be the product. Whoever's your anion, which in this case is sulfur, your electrons are going to be a reactant. So the cation, the electrons are a product. The anion, your electrons are a reactant. It's kind of like a pattern. It'll always be the same way. You guys will get good at this as we write more and more of them. Okay. So, those of you who couldn't read my handwriting, magnesium, we get 2 electrons, shows a loss of electrons. Sulfur shows a gain of electrons. So who did oxidation? Who did reduction? Correct. Yes, Casey. Yes, typo. Typo. Q plus. Alright, so this leads us to something called oxidation numbers, which you guys honestly already know how to do. Okay, do you remember in chemistry when you guys had to figure out charges? Not all the charges were always told to you. Sometimes you had to look at who it was bonded to. That's basically what we're doing right now, except we can't always look at the charges because we know that carbon and oxygen can both bond together, correct? Well, those are both nonmetals, so they're not going to be a positive negative charge like we're used to. We're used to doing charges with metals and nonmetals, correct? So today we're going to learn how to do something called an oxidation number, which is the same kind of concept except not everything is always charged. So oxidation numbers are used to help keep track of electrons in redox reactions. So in any reaction, okay, so in any reaction, an increase in your oxidation number of a substance indicates oxidation. So if our oxidation number is rising, if it is getting bigger in a reaction, then we're going through an oxidation reaction. If your oxidation number is decreasing, getting smaller, again, oxidation number, charge, similar concepts, not the same thing. If your oxidation number is getting smaller, you are going through reduction. If there is no change in any oxidation numbers, then you're not doing a reduction reaction. You're probably doing something like a double replacement reaction. Okay, double replacement reactions, they just switch places, right? So we're not, did their charges change? No, so we're not going to have a redox reaction because no oxidation numbers were changing. So it's probably not going to be a redox reaction. So there are rules for oxidation. So first of all, and you have to do these rules in order. Oh, sorry. Numbers, and again, you have to follow them in order. The first rule, atoms in elemental form will have an oxidation of 0. This includes your diatomic molecules. So for instance, the oxidation number of H2 is 0. The oxidation number of O2. What about copper? 0. What about iron? 0. Anything in elemental form. So if I go give you a sample of copper like we did in the lab last week, that is just plain copper. It has an oxidation number of 0. Okay, so that's the first rule. The second rule is monatomic ions will have an oxidation number equal to its charge. So this would be like if we're dealing with like magnesium oxide. Monatomic, we're dealing with one atom of magnesium, one atom of oxygen. We're not dealing with polyatomic ions. We're not dealing with multiple things. Monatomic, we're basically non-polyatomic. Okay, it doesn't mean that we can only have one magnesium, so it could also be like Li2O. Okay, it doesn't mean that there only has to be one of them. It just means no polyatomic ions. So is there a monatomic ion? Yes. Magnesium has a charge or has an oxidation number equal to its charge. So magnesium, second column, its charge is 2+, its oxidation number is also 2+. Okay, the third rule, oxygen has an oxidation number of -2, unless, here comes our first but, oxidation does not always carry its charge if it is a peroxide. If it's a peroxide, then it will be a -1 charge. We're not always great at identifying peroxide, so the way I can always just tell you to know if something's a peroxide, does it look wrong? So like for instance, let's come up with an example. So let's see here, like we know that Li2O, we know that we need 2 lithiums for every 1 oxygen because oxygen usually has a charge of -2, right? But if we're dealing with a peroxide, it would probably be LiO2. That doesn't look right, correct? So therefore, now our oxidation of oxygen is probably not going to be -2. How do I know that right off the bat? How do I know it's violating the third rule? Because if you look at that, that doesn't look right to you. Red flags went off as soon as I write LiO2. Does that mean it will never happen? No, it happens all the time. Okay, it's just we're dealing with a redox reaction now. Is it going to happen in a single replacement reaction? No. Is this going to happen in a combustion reaction? No. Is this going to happen in a combination reaction? Probably not, but it will happen in a redox reaction. Okay, so let's look at the next rule. The fourth rule says hydrogen has an oxidation number of +1 when it is bonded to nonmetals, but we all know that hydrogen can be both ways, right? It can act as a metal, it can also act as a nonmetal. So when it is bonded to metals, it gets to be negative, so it gets a charge of -1. Okay, it can gain and lose electrons. The fifth rule, halogens. Halogens are usually -1. We all know that halogens are in the 7th column next to those noble gases. We know that their charge is -1 because they will usually steal 1 electron to follow the octet rule, correct? Okay, so usually -1 unless they are combined with oxygen. If they're combined with oxygen, then they will be positive. For example, we have seen the polyatomic ion. We've all seen that, right? Okay, so in this polyatomic ion, is chlorine going to be negative? No. Who is going to be negative? Who's going to win this battle? Who has a stronger electronegativity? Oxygen. So oxygen gets to carry the negative charge, which means that chlorine has to be the positive charge. So chlorine is not always going to be -1, specifically when he is bonded to oxygen. Okay, the last rule is for oxidation numbers will always equal 0. So if we have a compound, the compound as a whole has to equal 0. Just like when we were doing charges, right? If we had iron oxide, we could determine the charge of iron based on how many oxygens we had, correct? Same basic concept. If we know what some of the oxidation numbers are, we can figure out the remaining because it all has to equal 0. But if you look at the bottom part of this, we also can do this with polyatomic ions. So a compound will equal 0, but if we're dealing with a polyatomic ion, it'll equal the charge of the ion. Okay, so not always 0 because sometimes we have polyatomic ions in there. So polyatomic ions, they will be, so instead of setting it equal to 0, we're going to set it equal to the charge. So basically, in order to determine people's oxidation numbers, you have to do a little bit of algebra. Don't worry, I'm going to do examples. Okay, so let's do an example. The first example says determine the oxidation number of each element in sodium sulfate. So, in order to do this, we're going to ask ourselves a few questions. So, first of all, is this substance elemental? No. Nope. There are 3 different elements present, right? Okay. Is this substance ionic? Is there a metal and is there a nonmetal? Isn't the definition of ionic? Is this an ionic compound? Yep, there is 1 metal and actually 2 nonmetals, so therefore this is an ionic compound. The next question is, if the substance is ionic, are there any monatomic ions present? So basically, is there something in there that's not? Is there a polyatomic ion present? Yes. Is there something that's not a polyatomic ion? Yes. Who is not a polyatomic ion? Sodium, which means that sodium has to have a charge of +1 because it's following that monatomic rule. We look at the periodic table, sodium's in the first column, so therefore it has a charge of +1. Okay, the next question we have to ask ourselves are there any elements that have specific rules? So we've already designated sodium as +1. So now we need to look at sulfur and oxygen. Is there a rule that talks about sulfur? No. Is there a rule that talks about oxygen? What does the rule about oxygen say? Are we bonded with somebody from the 7th column? Nope, so that's not going to apply. The rule for oxygen says oxygen has an oxidation number of -2 unless it's a peroxide. Is this a peroxide? Doesn't look like one, so oxygen's going to have what kind of a charge? -2. Okay. So we've designated sodium, we've designated oxygen, right? So now we have to do a little bit of algebra to figure out sulfur. Sodium is a constant, oxygen is a constant. Sulfur, we know that sulfur can do S8, so we already know that its charge can change, correct? So now let's figure it out. So, am I going too fast for me? And do you have to ask yourself these questions every single time? No, as you start doing this, it'll just happen automatically. But until we get good at this, we'll ask each other. We'll ask these questions, okay? So let's see if we can figure out the oxidation number of S. So basically what we are going to do, we know sodium equals 1 plus. We know oxygen equals 2 minus following the rules, but we do not know what sulfur equals. So all we're going to do is a little bit of algebra. Okay, we know that this compound is Na2SO4, correct? And this is a compound, so we have to set this equal to 0, 0, because it's not a polyatomic ion, right? So we're going to do Na2, so 2 times 1 plus, correct? Plus sulfur, we don't know what the charge of sulfur is, plus, and then we have SO4, so 4 times our charge of 2 minus, and we know that this has to equal 0. So now can we solve for S? Yep. 2 times plus 1 is 2, plus sulfur minus 8 equals 0. Move the negative 8 over here, that becomes 8, subtract by 2, so sulfur is going to equal 6 positive. So the charge on sulfur is 6 plus, which is its oxidation number. Is that its charge? No, because the charge of sulfur should be 2 minus, but this is a redox reaction, so we don't always have charges. Sometimes we have oxidation numbers, so the oxidation number of sulfur in this case is 6 positive. Okay, so let's do another example. Okay, so this time we are going to do potassium K2C2O4. Now, this one's not as obvious to you guys, but is C2O4 a polyatomic ion? Do you want to remember what it is? Oxalate. Carbonate is CO3. This is oxalate. It's a polyatomic ion. Probably not one that we recognize right off the bat, but we're going to do the exact same thing. First of all, ask their questions. Is the substance elemental? No. No, there are 3 different elements present. Secondly, is the substance ionic? Yes, we have metals and 2 nonmetals, so this is ionic. If the substance is ionic, is there any monatomic ions present? Is there anything that's not a polyatomic ion? Yes. Okay, so automatically that tells us that the oxidation number of potassium is 1 positive, because why? Because of the rule, it's in the first row. The first row has a charge of positive 1, correct? Okay, so now let's keep asking ourselves some more questions. Next question. Do any of those elements have specific rules? So now we're left with carbon and oxygen. Is there a rule that talks about carbon? No. Is there a rule that talks about oxygen? Yes. What does the rule that talks about oxygen say? Peroxide. It's 2 minus unless it's in a peroxide. We're not in a peroxide, correct? Okay. So, therefore, it means oxygen has an oxidation number of -2. And then, what do we have left? We found a rule for sodium. We found a rule for oxygen. So, the one we have left is carbon. So, now we have to figure out the oxidation number for carbon. So, basically, we're going to do algebra all over again, correct? So, we know that potassium equals 1 plus. We know that oxygen equals 2 minus, but we do not know what carbon is going to equal. So it's K2, so we're going to do 2 times 1 plus C, but it's not just 1 C. How many C's do we have? 2, so we have to represent that. And then we have 4 oxygens. And what are we going to set this equal to? 0. Okay, and then we just do algebra. So we're going to do 2 plus 2c minus 8 equals 0. You move the negative 8 over, which makes it 8. You then move the 2 over, so then we're going to get 2c equals 6. Then we divide each side by 2, so we're going to get carbon has a charge of 3 plus. Is that what the periodic table says? No, but this is a redox reaction, so they don't always follow the rules. Yes?
Okay, I'm confused with the whole polyatomic ion thing, because we have a polyatomic ion, so there's a rule about polyatomic ions and non.
But this is a compound. This isn't a polyatomic ion. If I wanted to figure out the charge of carbon in oxalate, I would set it equal to -2. But it's not just all by itself. It's part of a compound. Does that make sense? Does that answer your question? Yes. But it's bonded to potassium, so it's no longer, we're not going to set it equal to the charge because it's bonding to potassium to become 0. Okay, but we will do an example where we have to use that rule in just a second. And we're going to do one of those in just a second. Okay, so let's do some examples without the questions. Let's just see if we can do these off the top of our head. So let's look at number 1. Number 1 is barium nitrate. So, right off the bat, let's see if we can do this without asking ourselves some questions. Can we figure out a charge of somebody? Barium. What kind of charge does barium have? Why does barium have a charge of +2? So in the second column, he's following the first rule, or not the first rule, but it's an ionic compound, so we can look that up, correct? Okay, non-monatomic. So now we're left with nitrate. So we have nitrogen and oxygen. Is there a rule? Oxygen has a charge of 2 minus. So now we can solve for nitrogen, correct? So we're going to set up an equation. So we're going to take 1 barium, so 2 plus, which we don't have to write plus, we can just write 2. Okay, but do we have 1 nitrogen? We have 2 nitrogens, so we have to show that. So 2 nitrogens. And do we have 3 oxygens? We have 6. And what are we going to set this equal to? 0. So 2 plus 2n minus 12 equals 0. So we're going to get 2n equals 10. So nitrogen is going to equal, I have an oxidation number of 5 positive. Whereas if we look it up in the periodic table, it's 3 minus. Well, you move that over there so it becomes positive 12. Okay, so now let's look at NF3. NF3, is that ammonium or ammonia? Neither. Okay, so NH4 is ammonium. This is NH3, so this is NF. Oh, sorry, NF3. Wow, why did I go to ammonium? I looked at the next one. Number 3 is ammonium. Yeah. Anyhow, NF3. So this doesn't include monatomic. This doesn't include oxygen. So we're going to have to use a different set of rules, correct? So we're going to have to use the rule that deals with halogens. What does the rule that deals with halogens say? Halogens have a oxidation number of -1 unless they're bonded to oxygen. Is he bonded to oxygen? No, so that means that he has an oxidation number of -1, correct? So now we have to figure out nitrogen. So N plus 3 times -1 has to equal 0. That means N minus 3 equals 0, so N has to equal 3 plus, which usually nitrogen has a charge of 3 minus. 3 plus. But again, this is a redox reaction, so we don't always follow the rules. So now let's do this hard one. Number 3 is a hard one. 3 is ammonium sulfate. So do we have any monatomic ions? No, so we can't use that rule. Do we have any halogens? No, so we can't use that rule. We do have oxygen, so we can use that rule. Oxygen has a charge of what? 2 minus. Is there also a rule that deals with hydrogen? Plus 1 or minus 1 depending on who he's bonded to. Hydrogen is now bonded to a non-metal, so what kind of charge does he have? Correct. So now he is plus 1 because he is bonded to a non-metal. So we have 2 that we don't know. We do not know sulfur. There's no rule for sulfur, correct? And we also do not know nitrogen. There's no rule that's dealing with nitrogen. So we have 2 unknowns, right? So do you think we can do algebra with 2 unknowns very easily? We're gonna figure out nitrogen, and then we're gonna figure out sulfur. So we're gonna use the rule dealing with polyatomic ions. What's the charge of ammonium? Plus 1. What's the charge of sulfate? Minus 2. So now let's solve for nitrogen. So we need to know the oxidation number of nitrogen. We know that we have 4 hydrogens, and we're not going to set this equal to 0. We're going to set it equal to plus 1. Why? Because ammonium has a charge of plus 1. Why is that subscript there? To balance it with sulfate. So are we going to use that with when we're just solving for nitrogen? No, that subscript's there to make it a neutral ionic compound, right? Okay, so how do we solve? What do we do now? Okay, nitrogen plus 4 equals 1. So nitrogen is going to equal 3 minus. So now let's try to do sulfur. Sulfur, we don't know. So sulfur plus 4, we know oxygen is 2 minus, and this has to equal its charge, which is 2 minus. It's a polyatomic ion, and polyatomic ions, we don't set them equal to 0. Okay, so S minus 8 equals negative 2, correct? So then S is going to equal 6 positive. We add 8 to both sides. 8 minus 2 is 6. So sulfur has an oxidation number of 6 plus. Nitrogen has an oxidation number of 3 minus. So this was using that last rule. Okay, we had 2 unknowns, so we couldn't set it equal to 0, even though now we could set it equal to 0 and check our charges, couldn't we? Now we could use the subscript of 2 after ammonium to check to make sure we were right. Just check and make sure everything is equal to 0. So how do we feel about this? Not too bad. We just have to remember the rules, correct? So look how many examples I gave you. No, but you will memorize them just by doing them. I mean,